Okay, hi. So, as Michael said, I'm Ryan. I have this company in Gradientspace, except on Monday I started working at Epic Games, which I won't really talk about because I've only been there for like 3 days. Yeah, so my background, my research background was really in computer graphics with kind of like a minor in HCI. So I built lots of user interface systems, but more on the graphics side. So building like tools for doing 3D designing, making shapes on computers. That's usually how I describe what I did. So I worked on procedural shape modeling. I worked a little bit on geometry processing algorithms. I built lots of 3D design tools. I built this. This is like a 3D drawing tool. The one up there was a tool called Shape Shop for like moving around implicit surfaces and kind of making neat stuff. But mostly people, if they're familiar with what I've done, know of this software Meshmixer that I made, which was an Autodesk product, eventually, sort of. So if you're not familiar with Meshmixer, I won't assume you are. We kind of described it as a Swiss Army knife for 3D meshes. So if you have a triangle mesh from like a 3D scan, or you made it in a CAD tool, you might want to do things to that mesh. And there's not a lot of tools for doing that. And so we built this tool. I started in my PhD, and we just kind of added to it over time. So it does all sorts of things. It does 3D scan cleanup, mesh repair. I'm printing utility stuff, 3D sculpting. It has this drag and drop 3D modeling. I'll show you examples of all of these things as I go through. So like I said, it started during my PhD. I did this at first, which was sort of a demo for a paper that we released online in 2009. And people just started using it. In 2011, Autodesk acquired it. By 2016, it had been downloaded over 1 million times, and it had thousands of people using it every day. This is a picture that someone from Autodesk posted on Twitter. This is downloads in 1 month in 2017. So really all over the world, people use this software, even though it's not localized anywhere except English, Japanese, and Chinese. There's no other languages, but people all in these, like in the very far reaches of Russia, are downloading Meshmixer and making stuff with it, which was sort of more surprising because it was never really like a real product. Like if you called up Autodesk support and were like, hey, I'm using this product of yours, Meshmixer, for the first like 6 years of its life, they'd be like, what's Meshmixer? We've never heard of it. It was developed in the research group by me and then a team of me and another person. There was no sales or marketing. There was not really official support. There is now, but there wasn't for most of its life. And so this was kind of fun for us. I mean, we saw it as a research experiment, less than, not so much as developing a real product. But it was really driven by like the users of the product and like what they wanted to do with it. So when we started out, after I made the dragging and dropping parts, we added 3D sculpting. And this is very early, I think in 2012, we did a workshop with this organization, Girls Learning Code in Toronto, where these are like teenage girls doing 3D sculpting. Then they would 3D print the things. It was kind of fun. But then once we had the 3D sculpting, then more serious users came along and were like, we want to make this have, it needs this feature, it needs this feature. And within a year, we had like people making stuff like this in it, which we would have never thought that was possible. Once that started happening, then they started using it to clean up 3D scans, and then 3D printing came along. And in 3D printing, you're always 3D printing meshes. And so we started adding 3D printing tools. And so this was our sort of most well-known tool is for generating, if you ever used like a MakerBot, you need these like support structures that you have to break off. So the ones that come with the printer, if you try to print something like this, it's impossible. You'll break it trying to get the support off. So we made this like very sparse supports that it still took like half an hour to get them all off, but you can actually do it. And so that was a very popular feature. And then from there, we added all sorts of other 3D printing stuff. And that's why there's those people all over the world using it. Like I said, there was no support. So the users supported it, which is always a horrible thing to say about a product that like, oh, the users did it. But we had really amazing things happen. Like this was a Kickstarter. There's a company in Berkeley called Honeypoint 3D that was like a 3D printing shop. They ran a Kickstarter to make tutorial videos where they raised $14,000 and made this tutorial series that now I think like 9,000 people have bought. Now there's videos all over the place. On lynda.com, you can get Meshmixer tutorials for doing stuff. And on YouTube, if you go on YouTube, it's kind of crazy. But this is actually old now. When you search, it says 35,000 results. These searches always come up with all sorts of stuff. But there's a ton of videos on YouTube that people make Meshmixer tutorials and showing you how to use features and stuff like that. They submit bug reports with videos on YouTube. And we started to find over the years, like more and more serious stuff. So like it started out as a lot of these videos, like this top video here is this guy, Maker's Muse, who just tries out 3D printers, and he's like a video blogger guy, I guess. But these are videos made by dentists, and like real dentists. These are dentists who have 3D printers in their office, and they do 3D printing procedures, or like dental procedures using their 3D printers. So like if you go, this guy, 3D dentist, he's got a whole series of videos of using Meshmixer to do these dental procedures. And they just post them online, like this is how you, let's see, like this top one is if you want to remove someone's tooth, they make this jig they use and stuff like that. I mean, if these are long videos, and they're very, like, actually there's now 2 dentists that teach, they essentially teach courses. They teach like digital dentistry courses that are basically like a Meshmixer and a Formlabs printer. It's kind of crazy. This is a project from UMB where they do these kind of tooth replacement surgeries where they make these 3D printed jigs. They design them, you know, they take a scan of your mouth, they design this jig. This is a little, I mean, I don't want to describe it because you have to think about it, but like the top one there is a jig where they're basically cutting off the person's lower jaw, and then these are implant guides where they're going to put in screws and then they're going to implant a set of teeth. You know, I love these projects. I mean, there's a ton of like maker projects where people are doing fun stuff with it. But I love these projects because they always, for me, are like when someone would say like, wasn't 3D printing over? You know, that came, it happened. It was on the top of the hype curve. It's over now. But it's like, it's really not over. All over the world, people are using these machines, these like consumer level machines, and using 3D printers and using these kind of weird design tools to do all sorts of stuff. So Toronto General Hospital in Toronto is not unique anymore in that they have a 3D printing lab in the hospital. This is now becoming a very common thing that a hospital has a 3D printing lab. And what they use them for, so like this is just a print of someone's CT scan. And the surgeon will look at that before a surgery just to make sure that like their mental model of what's going to be in there when they open the person up is right. And I've been to conferences where you hear these stories and you're just like, oh my God, what's happening? In these hospitals where like the surgeon was on the way to the operating room and stopped into the print lab and the print just happened to finish in time, and they look at it and they're like, oh, that's not what I was expecting. And they put it back and go to do the surgery, right? But that's happening now. That's a thing that happens. These other 2 here, so these here, this is a print of someone's skull. Obviously what they're doing here is they're pre-forming these little metal, it's hard to kind of see, but they're little metal grids that they're going to use during the surgery. So otherwise they have to do that on you while you're cut open. They have to form those things on you, which then, you know, there's more risk of things going wrong the longer you're cut open. And so they can do it now on like a 3D print before those things happen. So it's actually not, I mean, it's not on the hype curve. This is really being done, not just experimentally. I'm going to tell you about 2 projects now, basically, for the next chunk of the talk. In more detail, 2 of these projects. I just think these projects are super cool, and they're going to illustrate the rest of my talk. This one is done by a lab at University of Buffalo. They have a kind of experimental hospital where some floors are a functioning hospital and other floors are biomedical engineering research lab. Chip Ioannidis there, his lab does this project I'm going to tell you about. So my only involvement in this really is that I kind of gave them some advice on how to do stuff in Meshmixer, but I'm going to tell you about the whole project because it's kind of amazing. So if you have like an aneurysm and they want to do minimally invasive surgery, what they do is they feed a catheter, which is basically a wire inside a tube, up through your thigh, and they like steer it through your blood vessels up into your brain, up into the aneurysm, and then they fill it with this platinum wire. And so what that does, they fill the whole thing, and that coil causes the blood flow to reduce in there. So the aneurysm is basically like a bubble, and if it pops, bad things happen. And so that, once the coil's in there, the blood flow slows down in there, and then it clots, and then it kind of fixes itself. So the problem is they have to get this wire through all your blood vessels into your brain, which is really hard, and if like obviously if they poke the wrong place or something, bad things could happen. So they have to practice to get good at doing this. And so they have these simulators. It's kind of funny, they're almost like a video game. I got to use one, and it's like, it's physical setup, but like you're just kind of turning this wire and steering it. I mean, obviously when they're doing it, it's very serious, but it is also, I'll show you what the whole thing looks like. But here, this is the simulator setup where basically This is supposed to be like what's inside your head, the blood vessels that they have to steer through, or those are the hard ones. This is like where they feed it in in your thigh, and the catheter goes up there, and then they have an X-ray set up. So I'll show you on the next slide. But this is you can kind of see here the wire in there. It is literally basically a little wire. It's a little tube. And the way the person does it, so they stand down here. I mean, they're standing down by your knees, right? And they're looking at a screen up here. That's where your head is, right? This is a big X-ray machine. And that's what the X-ray they see up there, and that's what they're looking at. So that's why I say it's kind of like a video game. You see this, basically, and you can kind of see the wire. I don't have a nice video of this. And you're trying to basically like steer the wire through these blood vessels. And what you can do is you can like push and pull and turn it. And then there's a little trigger where you can kind of cause it to bend at the end. So, I mean, obviously this is hard. Because this is what you see, right? The blood vessels are this complex 3D network, but this is all you see. You see this 2D projection with this kind of fuzzy overlapping. So, and I mean, when I say they want to practice it, they couldn't really practice it. You could practice on like standard models of these things, but the idea of just like fabricating like if they take me in there, and I'm like, well, we just want to make my brain blood vessels in a little plastic thing that we can practice with. I mean, how would you do that? You couldn't do that before. Now they can do it with 3D printers. So they make this Vascular Phantom, it's called. And this is the Meshmixer part now. They essentially, starting from the scan, they like make that thing. And it's like conceptually, it seems kind of straightforward. You have the scan, you pull out this geometry, you make a mesh, you 3D print that mesh. This part here is actually quite complicated of how you do it. So they have tutorials, essentially, which they publish as research papers. So this is a paper, I can't remember the name of the conference they had this at, but essentially it's a tutorial, and it's kind of, for me, it was a bit embarrassing to read this paper, because like there's a whole section in the paper about dealing with mesh errors. These are essentially my bugs. Like, I made mistakes, so now they have to have sections of their paper about how they compensate for my mistakes. Yeah?
This is really cool. Are the 3D printers fine enough to print something as fine as like something that would go in your head, or is this to scale?
It is to scale, yeah. So they simplify a lot, because you don't, the catheter also doesn't go in the very tiny blood vessels. Generally, I think the aneurysms are mostly on the larger blood vessels that you would want to deal with. And so so you see here, from here, they removed a lot of the blood vessels. It's the same, or maybe this isn't the same model. But all those little ones, they take out. That's part of the process, because they can only make stuff at a certain scale. The walls have to be kind of thick enough. There's a whole aspect to this that I don't know that much about, which is to do with like the pressures of the blood in the blood vessels. And so that's another factor. It has to be somewhat realistic material-wise. But the net effect is they can make these things, and they use them. So this is a person from a video Stratasys made who actually had this surgery done on her. That's her brain blood vessels she's holding that they used. And in the video, the doctor says, like, it's a good thing we did this practice, because in our initial plan, we found some problems. And so it's a good thing we had the system. And so, I mean, for me, the interesting thing here is like this printer existed long before they did this project. This wasn't really a new thing, but what they had been trying to do is they've been trying to make these complicated shapes using like mechanical engineering CAD software. For many years, they tried to do this, and it just hadn't worked. It's too hard to make these things. So we gave them like a new tool, and the tool essentially came out of this maker community of like tools for teenage girls to do 3D sculpting, and now they're using it to do this brain surgery planning type stuff, which I think is kind of interesting. And this is another project I worked on. This is the project with University of Toronto, so I was much more involved in this one. So Matt Ratto there at the Critical Making Lab, he kind of drove this project. And this one is actually, I mean, in some ways totally different use case, but at the conceptual level is almost the same as the previous project. So we needed to make legs, essentially. So if you lose a limb here, or if you're born without a limb, and you go to get a prosthetic, what you get is this quite fancy, this is like usually carbon fiber socket, CNC milled. You get nice aluminum parts and stuff like that. If you are in Uganda, what you get is something more like this. So this is a hard plastic shell, hard plastic connectors and stuff like that. This is the standard Red Cross process for doing this. So this is the process that like Red Cross will give you money to do is essentially all based on plaster casts. So they take a cast of the limb, that's the negative, then they make a positive. They use this is a pizza oven that they use to heat up this sheet of, this starts out as a flat sheet of, I think, PVC plastic. And then this is a vacuum forming machine. So the plastic, the positive there is on the end here underneath. And they vacuum form that on top, and then they kind of like grind at it with Dremels type tools and stuff like that until they can attach it to that plastic stem, which is a standard part. So this works, and works fine. The biggest problem with it is that, for instance, when we were doing this, in Uganda, the entire country, that's 36 million people, there was 12 prosthetists, which is not very many. Like Canada is a similar number of people. We've got way more than 12. Still not enough, but a lot more than 12. It takes them about a week to make a leg, waiting for all the plaster to dry and doing the stuff they need to do. If you're a kid, then you're growing, so then you need your legs changing size, so you need new ones all the time. So it's not really a problem of like the technology. We don't need like higher tech prosthetics there. What we need is just more of them, just like a lot more prosthetics. The biggest problem is access to care. So the World Health Organization estimates that 40,000 prosthetic technicians are needed globally. I can't remember 100%, but I think that's actually more than there are right now globally. So the idea that we're going to just generate tons more prosthetic technicians very quickly seems unlikely. And so actually the hospital in Uganda came to us and said, like, could we use these new 3D printers to make these hard plastic shells that we make now with the pizza oven and the vacuum forming, right? And we kind of, I thought, like, obviously, of course we could. Why not? It's just a hard plastic shell. But it's more complicated than that in practice. I'll tell you about it. But essentially our goal here in this whole project was to develop this process for making these things. And the critical thing there was that it's usable by the prosthetists, not by me. Like, I can do it in Meshmixer, but like, could a prosthetist do it? Ultimately, the actual practical was to say it's not going to take you a week. It's going to take a day. So you can come in, get scanned, and you'll leave with a prosthetic that day. That was the goal. So like I said, you start out, we scan. It's not complicated. We use these off-the-shelf, like this is a 3D Sense scanner, but this essentially is the same thing in it that like a Microsoft Kinect does. Right? It's not the most accurate, but also prosthetics are not the most accurate. And you have to clean up the scan and stuff like that. And then the modeling process is not that complicated. You have this scan of a limb. We make this kind of plastic shell around it. You attach this connector at the bottom, and that's essentially a prosthetic. You attach the standard piece to the bottom of there. In Meshmixer, we had all these tools that we could kind of assemble into a workflow for doing this. This is a demo video of me doing almost the entire thing in 30 seconds. I think it's playing at 2 or maybe 4x, but it doesn't take very long. Essentially, you need to make that curve at the top the right shape. Now, this is me doing it, so this is completely wrong. This is not what a prosthetist would do. And that's an important thing, actually, that we learned in this project. You've probably seen maybe even on like public media, like other prosthetic projects. Don't just make prosthetics. It's very dangerous. You can really harm someone by just making them a bad prosthetic. So it's very important that actual prosthetists are involved. And that's kind of why we have to make the thing usable by them. We also did lots of mechanical testing for the same reason I just said. You don't just want to put these things on people without knowing that they're going to be safe and stuff like that. So they did this robotic testing, and like these are Instron machines where they just physically destroy it to see how strong it is. And then we went to Uganda. So I went on the first trip. There's been quite a few since then. And basically we took all this like high-tech stuff to these labs. Well, this was the first lab where essentially, the most sophisticated equipment here was the pizza oven. Most of the stuff is hand tools. They're doing this all with hand tools. And we made prosthetics. So this was our first patient, essentially, Rosaline. She was a 6-year-old girl. And this was the leg one of the prosthetists there designed for her. I printed on the MakerBot. We had a bigger printer, but the power kept going out. So this was the perfect size. It just fit in the print bed. They put the leg on it, and then she could walk on this prosthetic. And it fit well. We had an older girl who basically said she thought these fit better than the ones they had been making, which wasn't our goal, but we were super excited with that result, right? And this became this company, Nia Technologies now, which is I guess the website isn't on there, but it's at niatech.org. So they did 4 clinical trials at different sites in Uganda, Tanzania, and Cambodia. There's over 200 kids wearing these prosthetics now, and they're currently making a new version I'll talk about a bit more, which is currently being tested at Sunnybrook Hospital, which is a hospital in Toronto, and I think now they've done a deployment of the new system in Tanzania. So they improved the printing, all sorts of stuff. They changed materials, they experimented with all the different things, and it got much better. And so, I mean, I've told you about some of these different projects, and I mean, I really love these projects, and they really nicely illustrate like the use of these new printers and things like that, this new technology that's come about. But also, I can look at these projects and see that quite a few of them are kind of stuck in a stage, and I'm going to talk about that for the rest of the talk, about what the sort of problem is still in this concept of like that you could take this these new machines and this new types of software we've made and somehow provide that to people in these new domains. That's not actually working that well yet. I'm going to talk about this one specifically. So this project now has been going on, I think, since 2014. I mean, it's amazing. They do like brain surgery with these things. It literally saves people's lives. But they only do it at the one hospital in Buffalo. And part of the reason for that is this complicated workflow I described before. So it's sort of, on the one hand, it's not that hard to do this, but on the other hand, it's really hard, right? Like a technically sophisticated computer science student can figure out how to do this. They have a lab there of biomedical engineers who are now essentially medical or Meshmixer experts, and they're the ones who make these things. But not every hospital has a lab of biomedical engineering students who are experts at this who can make these things. And so, you know, what they would like to have is a tool that would make that easier, and that doesn't exist yet, and I'm going to explain why that's not happening yet. So how do these projects happen? I've looked at a lot of these projects. We saw a lot of them with Meshmixer, and there's a kind of almost life cycle that they go through, right? And the first thing that happens is they have a workflow, right? Someone figured out how to use these tools and these machines to produce this thing from their inputs or whatever, right? And so this is a nice slide I found. I came across at Autodesk. So this person, Tatiana Zambizova, she's from Autodesk here in San Francisco, or was. I don't think she's there anymore. But she made this software called PhotoFly, which became 123D Catch. That's the, like, if any of you ever used it, it was their cell phone scanning app where you could take pictures of something and it would make the 3D shape. So they had a higher end version that Louise Leakey, who's like a very famous anthropologist, I think, was using. So this, it's kind of fuzzy in the pictures here, but oh, you can see over there. This was like a skull that they've got somewhere in Africa, and this, they want to do like a 3D reconstruction of it, right? So this was their workflow. You can see there's arrows going backwards. It's very complicated. I mean, the app makes some things seem really simple, but if you care about the science, if you care about like being able to take measurements off this precisely and stuff like that, you know, you end up having to go from this tool to this tool back to this other tool. And this is pretty common. I don't know how many of you have ever like had to solve a like kind of real problem using these kind of any of these CAD tools, really. You often end up going between things and stuff like that. And so we call those workflows. And workflows are fine if you are like you have to do it. But they're not fine if it's kind of optional. And that was the thing we kind of came to realize is that like a lot of the people who want to do this stuff, they're not engineers. They're not really makers either. They're not like tinkerers. These are professionals, like professions like prosthetist or medical doctor. And they don't want to learn how to do this. Right? Like I showed this video before. I mean, it doesn't look that hard. But if you don't know this software, if you didn't invent it, like I did, then all these things that appear are confusing, like which thing. I'm using hotkeys here. You don't even notice, maybe. I'm changing like one slider and not the other one. Right? Like learning how to do this takes a lot of time for anyone. You can be trained on it if you can find someone to train you. But like if you're a working prosthetist, you're busy making prosthetics, and being trained to learn some CAD tool is not what you do. A lot of these things, like I mentioned, the dentistry ones, the way that actually happens in dentistry, where there's a lot of 3D printing already being used, is they hire a technician who does it. And then they talk to the technician, and there's all this translation error. And technicians are expensive. And so then there's all this friction in making these things happen. So then often it doesn't happen. So then the next thing that tends to happen after you have this workflow is people start to think like, well, maybe we could make a plugin to one of these existing tools, right? We did that in the prosthetics project, actually. The first version, like when we went to Uganda, we had this thing we called the Wizard, which was like this separate as a browser thing that could talk to Meshmixer. So it would automatically start the tool you needed. And it was better, but it still didn't really work. So here, this little text field over here that's going to set a parameter of something that happens over there. But I mean, if you can maybe already see the problems, like what if I make a mistake? Well, this thing, I mean, it could go back sometimes. It couldn't always go back. Undo didn't work that well. What if I accidentally over here click and cancel out of something? And that's usually what happens with these plugins, is like you have to learn too much still. You still have to essentially learn the host app. You have to learn how to like rotate things and do all these stuff in that app. There's all this hidden state that's confusing, like the undo problem. And really, the host APIs often don't have very good APIs. They're not, I mean, maybe if it's open source, you could go in and change the source if you knew how to do that. But even that is a pretty tall order. And the interfaces you can actually build are usually not very good. So we've seen people try this, and it's basically doesn't seem like it's ever really worked. So then what you get to is like, oh, we need to build our own tool. And that is, I mean, it has happened every single time I've talked to people of one of these projects, is where they get to is like, we want to make a tool that's like our workflow exactly, this step, this step, this step. That's hard because every one of them is completely different, or it seems, right? If you talk to them, they're going to tell you it's completely different, and they need their own tool. Building these tools from scratch is a lot of work. I mean, Meshmixer, we didn't work on it continuously, but it took us like 7 years. So when someone would come and say, like, how hard would it be for me to build our own Meshmixer that just had these 3 tools? It'd be like, well, it's going to take you a long time, and you're going to need a PhD in computer graphics, maybe, which is pretty tall order. And then the other problem is a lot of these domains are small. So like this brain surgery thing, I mean, if you go and try and like raise money to build that, it's tough because you can't say like this is going to be a $1 billion industry. Prosthetics is not a growth industry, so it's really hard. The prosthetics companies, there was a sort of competitor prosthetics project, and they've already pivoted away from making prosthetics because it's just not big enough, and that's why these tools don't already exist. And so the sort of conclusion I came to is like we need some sort of infrastructure for doing this, where it is customizable for these workflows, but you can make interfaces for these non-experts. And I kind of wanted to do that with Meshmixer, but it's really hard to go back. Once you've built all of this stuff, getting rid of it all so you can just have 3 things becomes this huge software engineering project. And I mean, also, there's like business problems. Like Autodesk doesn't want to make hundreds of small apps for different industries, or at least I can't speak for Autodesk anymore, but at the time, no one wanted to do that. So I started this other company, Gradientspace, and that was really my plan, was like figure out how to make it possible for any developer to build a 3D design tool. So like not an expert developer, but just like someone who kind of can do decent coding. How could they make a 3D design tool? And not like a prototype one, but like a functional one that then you could give to a doctor, and the doctor could say like, I can basically use this except this bit here and this bit here, and you'd fix that, and then they'd be like, okay, now I can make these brain surgery things. That was the kind of the hope. And so I built all this infrastructure for doing that. I mentioned infrastructure before, so I built some open source libraries, this geometry library, this 3D printing library, and then this app framework. That's mostly what I'm going to tell you about. These are all open source with commercial friendly licenses. I mean, they have to be if people are going to make companies out of them. And that's an important thing. People often say like, well, couldn't it just all be open source? Open source developers do this. I mean, what the dentist wants is like a company they can go to that's going to come to their office and set everything up and give them a training course. That doesn't really happen with open source. It has to be companies because you have to do all this other work just to get the stuff out there. So open source doesn't completely work. I'll just mention a bit about the slicer because I know there's people here that do fabrication stuff. So the slicer is all entirely open source. There's lots of cool features. And the slicer and geometry library, I write tutorials on how to use them on the Gradientspace website. So if you're interested in that kind of stuff, I won't talk about it anymore, but you can find out more there, and happy to talk about it afterwards. But I'm going to talk about this framework a little bit more. It was called Frame 3 Sharp. I started a C++ version, and then I made a C Sharp one, so that's why it's called that. So this was meant to be like a design tool app framework. It's kind of what I called it. Sort of like I don't even know if people know what Qt is anymore. Maybe Electron. Should I say like Electron, but for 3D design apps? I don't know. I'm old, so I initially had Win32 there, and I know that most of you have never used Win32. I wanted to like be the standard library of all the stuff you need, right? So all the standard 3D tools, like those little XYZ axes things, you move stuff around, gizmos, new elements. I'm going to show you examples of these. Things built in, like if you want to undo and redo changes to 3D models, that should be in there, supporting the different places you want to have 3D stuff. So that's a lot of that is kind of built already. So the first thing I built with it, so then basically what I did is I built some tools to make sure that it was useful and working. And that helped kind of guide the design. So this is a VR app, sorry for the weird angle, or at least from where I'm standing. This is called Simplex. And this is basically like a simple VR design tool, but you can see it's got like bimanual interaction. It's got kind of a kind of heads-up display here. So in your headset, this is right kind of at a reasonable distance and stuff like that. And so it has these kind of 3D shape manipulation tools. I built this other app, Cotangent, which is a 3D printing tool, and it has some mesh repair stuff and things like that. So these are both going to become open source now because I have a new job and I'm not going to continue doing these apps at Gradientspace. I'll just mention that they're not open source yet, but they will be. But the ones that were kind of for me more exciting were two companies that I worked with to build the apps on this stuff. So there's this company Archform, which is a dental 3D printed, they're not 3D printed, dental aligners company here in the Bay Area. It's a startup. If you know what Invisalign are, they're kind of trying to do stuff like in the same direction as Invisalign. And Nia Fit, or these are the names of the products. So this is the prosthetics, Nia Technologies. So they made a new version of their app based on this framework. Actually two. So we made a VR version and a sort of desktop version. So this is a demo of the VR version. It's going to play automatically, I don't think so. HTC gave us some funding, and we made this VR one. So you can see now, this is the sort of more domain-specific tool. So it's, in some ways it's not that different, but like over here, the UI is just the exact tools they need. You can only do the certain things at certain times. This trim line, in the old one, I was like painting the triangles with a brush. That's not what they wanted. They wanted like a curve, they could say, and it should be exactly like this. And tools that are intuitive for them to nudge this curve around rather than like a bunch of control points that they would click and drag on. They have to make this socket at the end. They want to be able to like tweak the socket a little bit without having to go back. So this is, when I say domain-specific design tool now, this is as close as we could get to like exactly what they wanted. And then it's built on this framework. So we can take that and put it into a desktop app too. So they have a desktop and mobile versions. And it's not like, when I say the same, they didn't like cut and paste code from one to the other. This is like the actual, what happens in here is like a library that they can we could use in both of them. And then, and this is my best example of exactly what I wanted to happen. So this is the dentistry app. They needed to like segment the teeth. So they need to move the curves around. And this is the prosthetics app where they need to do this curve. This is the exact same tool. This never happens in CAD tools. You never have like a tool from Fusion 360 being just like copied into Inventor because those are completely different code bases, completely different architectures. You can't do that. And so this was sort of my goal is that like you would have a bunch of these tools as kind of building blocks you could kind of put together with UI, and you can make these domain-specific design tools. So that was the premise. You would have this library. You would have this other thing. Now I'm just going to tell you a bit more about how it was built. So it was built on top of a game engine. And this, I think, for me, this was really interesting. When I was at Autodesk, people would say, like, why don't you build Meshmixer on top of something? Because we had to do all the 3D stuff ourselves. And people had suggested this, and I was like, that's never going to work. That's a terrible idea. And then I left Autodesk, and then I built this thing on a game engine, and it really worked. And so I was wrong. And then partly the reason I was wrong was because like my concept of what a game engine did was not really correct anymore. Because when I was younger, I had done game-type stuff, and game engines were much simpler then. But now, I mean, this is a diagram is sort of schematic, but if you actually were to look at like the amount of code, it's like game engine is massive, and we're just putting a little bit on top. Modern game engines are crazy. They do like all the 3D stuff for you. They have amazing rendering. They can make like super realistic looking stuff in real time. They have cool physics. The really amazing thing at first for me was like you can put, if you make a thing in a game engine, it can go on any platform. Like if you wanted your CAD tool in an Xbox, you can do it. And I mean, that sounds like nonsense to most CAD people, but like there's like millions of kids who are 3D designers now in Minecraft, and like they use an Xbox controller or a PS4 controller. It's like, what would those kids do if we gave them CAD tools on a PS4? It would be very cool, I think. It has all support for all like when people make a new input device right away, they have like APIs in the game engines. It does the VR and AR, and it does all this real-time network collaboration. If you want to do like remote stuff, it's kind of crazy how easy it is in these tools. So I was thinking about this whole time I was doing these projects. It's not really totally the topic of this talk, but I thought I would just end with it. Because I think a lot about like, how do we make software? I mean, I make a lot. I've showed you like, I've built myself probably like 6 or 7 different quite large systems. And I've been involved in some other ones. You know, we had like PCs and we had these operating systems for them. And then we got these phones, these mobile devices, and we have these operating systems for them. And now we have these headsets we wear around, or could, right? I mean, that's the plan, right? We're all going to wear around these AR glasses. And we're going to do stuff in them, right? I mean, that's the theory, at least. We're not really building it yet, right? VR, mostly people building are building games outside of research labs. And for these kind of devices, people are doing a bit more of the AR goggles, but they're not really that ubiquitous yet. But like almost any time you look at these projects, they're building them on one of these game engines, on like Unreal or Unity. And so those are kind of like the operating system for these devices. They have all the stuff you need to make these things. And so for me, that's really interesting as a place to try and put this stuff that I was thinking about. And so, yeah. Can't say what I'm going to work on in the future, but maybe that gives you a bit of a hint. And so that's my talk. So thank you. I just want to tell you there's code on GitHub, Gradientspace. I do lots of support on there. If you want to use any of the libraries and you have questions, please don't hesitate. There's tutorials on the Gradientspace website also. All my papers, if you're interested in the research side of this stuff, you can get at my website, rms80.com, and I tweet things on Twitter there. That's my talk. Thank you.